Good morning. I welcome you all to this session of fluid mechanics. Today we will start a new chapter, a new section, that is fluid flow applications. We have already discussed the conservation equations, that is the conservation of mass, equations for conservation of mass, conservation of momentum and conservation of energy, and we have solved some problems related to finite control volumes, both inertial and non-inertial control volumes. Now in this section chapter we will discuss few practical problems of fluid flow applications, which will be solved on the basis of the equations for conservation of mass, momentum and energy, the applications of those equations. Better we can say that it is the application of conservation equations to fluid flow problems. At the outset, we will discuss little bit about the Bernoulli's equation or Bernoulli's theorem, which we have discussed earlier, a little elaboration on that. If we recall, we earlier recognized the Bernoulli's equation as the equation of mechanical energy or mechanical energy equation in case of a fluid flow, which tells about the conservation of energy in a fluid flow. And we have recognized that if the fluid is inviscid, obviously the mechanical energy remains constant. If there is no energy added from outside, no mechanical energy is taken out of the fluid, and if the fluid is inviscid, that means viscous action is not present, that fluid is inviscid, no viscosity, that means no friction. So mechanical energy cannot be dissipated in terms of intermolecular energy or heat, as you can tell. So in that case total mechanical energy remains constant, and we have seen that in general this mechanical energy, total mechanical energy remains constant along a streamline. And we have recognized different forms of mechanical energy as the pressure energy, kinetic energy and the potential energy. If you recall the equation, you can tell that P by rho, which represents the pressure energy per unit mass, plus V square by 2, which represents the kinetic energy per unit mass, we have to always recall in this form, plus Gz, where Gz represents the potential energy per unit mass. Here of course we consider only the Earth's gravitational force field as the only body force field. So therefore the potential energy per unit mass will be Gz, where G is the acceleration due to gravity and Z is the elevation of the point concerned, where we are considering the energy per unit mass from an arbitrary datum. So P by rho plus V square by 2 plus Gz thus constitutes the total mechanical energy, and which is equal to constant for an incompressible steady flow, because this form of the equation comes only for a steady incompressible flow. That is of course important, otherwise integral dP by rho will come for a compressible flow, but P by rho, this term comes for an incompressible flow. So for an incompressible steady flow, P by rho plus V square by 2 plus Gz, simply the sum of the three components of the mechanical energy is constant along a streamline. If you recall the derivation of this equation, we did it by integrating the Euler's equation along a streamline. Probably you can recall this, that integrating the Euler's equation along a streamline. So therefore the constant which came out of this integration was a constant, that means it was valid only along a streamline. So therefore essentially the mechanical energy varies from streamline to streamline in general. But now we will extend this in case of an irrotational flow. That means if we add a further constraint in the flow, that if the flow is irrotational, already you have studied what is an irrotational flow in fluid kinematics, that a flow is irrotational when the rotation at each and every point is 0. And you know the rotation of a fluid element at each point is defined as the curl of the velocity vector, curl V. In different coordinate system we can expand this curl V. Physically the rotation means the arithmetic average of the angular velocity of the two linear segments meeting at that point, which was initially perpendicular. So rotation is 0 means the flow is irrotational. So if we add a separate or additional constant of irrotationality, that means the flow becomes irrotational, inviscid, steady, incompressible, then this mechanical energy is constant throughout the flow field. That means P by rho plus V square by 2G plus Gz is equal to constant not only along a streamline, but at any point in the entire flow field. This we will derive first, which is a very simple derivation. Let us do it. Let us see this. Let us first take a two-dimensional case, a two-dimensional flow. a two-dimensional flow in a Cartesian coordinate system, in a Cartesian coordinate system, in a Cartesian rectangular, that is Cartesian coordinate, a Cartesian coordinate system. And in this case, let us consider only x and y, no z, so y we consider, and this we consider the y axis is in the vertical direction, y directed positive upwards, vertically upwards, so that g is acting like this. So if this we consider as the frame of coordinate, and also we consider a steady and incompressible flow, if we consider a steady and incompressible flow, steady and incompressible flow, then if we recall the equation of motion, that is the Euler's equation, we can write that for a steady the temporal derivative will not come, u del u del x plus v del u del y is equal to minus 1 upon rho del p del x, if you recall. So this is du dt, big du dt, big du dt. That means this is equal to minus 1 upon rho del p del x. This is the x direction. So this has been expanded. Del u del t is 0 for steady state, so I have not written. Del u del t is 0 for steady state, and rho is minus 1 upon rho del. This is the form x direction equation. Y direction equation similarly will be dv dt, if you recall, is equal to minus 1 upon rho del p del y. So if you expand this in case of steady flow, that means del v del t 0, then you get u del v del x plus v del v del y is equal to minus 1 upon rho del p del y. So these two equations are the equations for incompressible steady flow with respect to a two-dimensional Cartesian coordinate system. Of course, here I am wrong. Minus rho del p del y, here g is here acting. So we have considered the y-axis such a way that vertically upwards directing positive. So g is in the negative direction. So body force term will come, which will be here minus g, because these are the force per unit mass, because here this left hand term is the acceleration per unit mass. So first term on the right hand side is the pressure force per unit mass. So per unit mass the body force will be minus g. Why minus? Per unit mass it will be g, mg divided by mg, and it is in the negative direction of the positive y-axis. So therefore minus g. This comes as the body force. If you recall the body force, here the body force is 0. In the direction of x there is no body force. So we have chosen the y-axis in such a way that it is directed upwards, vertically upwards, so that the gravity force come as the body force. So per unit mass basis it appears as minus g. I am sorry, so this term will come. Now what we will do, we simply know that the basic approach for finding out the energy equation is to multiply the momentum equation with the displacement. So what we do, if we multiply this equation, x direction equation by dx, and multiply the y direction equation by dy, both these sides, and add it, what we get, u del x dx, we first take the u term common, then from this equation it will be del u del x dx, and from this equation it will be u del v del x dx. Okay. U del v del x dy, sorry, u del x dx plus v del v del u del v del x dy plus v del u del y dx plus del v del y dy. Okay, is equal to minus 1 upon rho, if you take common, then del p del x dx plus here del p del y dy. We are multiplying this equation by dx and this equation by dy and adding up u del x dx plus u del v del x dx, del v del x dy, I am sorry. Similarly, v you take common, del u del y dx plus del v del y dy, minus 1 upon rho del p del x dx plus del p del y dy minus g dy. Now After this, we put the constraint for irrotationality. Now for irrotational flow, that is the condition for irrotationality is del V del x minus del U del y, very simply 0. Now we pose this irrotationality condition mathematically on this. So if you pose this, now we just substitute del V del x as del U del y here, and here del U del y as del V del x here. The purpose is very simple, you will understand that this will become the first terms in the bracket del U del x dx. Del V del x is del U del y plus del U del y dy. Well, so it becomes del U del x dx plus del U del y dy. Similarly, here in place of del U del y we substitute del V del x. So del V del x dx plus del V del y dy, well, is equal to minus 1 by rho del P del x dx plus, sorry, this will be in the bracket del P del y dy minus G dy. Now it's simple mathematics. So therefore we can see that we have described the problem in two-dimensional in xy coordinates. So therefore this we can write as du. Why? U is a function of xy if we consider, then du is the change in u is caused by a change with both x and y. So mathematically by Taylor series expansion, neglecting the higher order term, we know that this we can write. Similarly, if we consider v as a function of xy in two-dimensional system, so del v del x dx plus del v del y dy, del v del y dy can be written as dv. Similarly, the case of p, that we can write this as dp. I am not writing it again. So dp. That means this equation can be written now u du plus v dv is equal to minus 1 upon rho dp minus g dy. Now this is the equation which we obtain. Now if we integrate this equation, what we will find out? We will find u square by 2 plus v square by 2 is equal to, now if we consider the incompressibility, the condition of incompressible flow, rho is constant, so we can take out of this integral. So integral dp means p, so minus p by rho minus g is constant plus y. That means we can write now u square plus v square means the resultant velocity v square, and we take p on one side, v square, v is the resultant velocity, where v is the resultant velocity, I u plus j v, where I j are the unit vectors in x and y direction. That means v square is u square plus v square. So capital V is the resultant velocity plus gy is equal to constant. Now you see that this is a constant where there is no restriction along a streamline. Why? Here this equation means that the summation of these two. Now you know, if we have a force vector f, and if we make a dot product, that means the scalar product with a position vector in polar coordinate dr, this implies the work or energy. This dr is dx and dy component. Similarly, what we have done, that equation of motions, if you see that the equation of motion, because force into distance is the work, similarly the equation of motions have been multiplied with the respective component, displacement component dx dy, and this has been added. That means this component dr is arbitrary, there is no restriction that whether it will be always along a streamline or so. So therefore in the entire deductions we have not made any restriction regarding this choice of dr, the arbitrary displacement, which we have multiplied with the force vector or the equation of motion or the equation for the conservation of momentum, so that this constant is a constant throughout the force field. So therefore now we derive or we come to a very general conclusion which is very, very important for you in the entire lifetime, those who will be dealing with fluid mechanics, that the total mechanical energy, that is the pressure energy, it is per mass basis written, kinetic energy and the potential energy is constant throughout the flow field in case of an irrotationality. So therefore, for an irrotational flow, the mechanical energy is constant throughout the flow field, which physically implies that the irrotationality to be maintained in a flow field, energy should not be added, energy should not be taken out from the fluid. So total mechanical energy remains the same. So therefore, irrotationality and the constancy of total mechanical energy in the flow field is a consequence of one another or each other. Okay. Now, after this we come to the definition of certain flows, certain important flows. First we start with plane, okay, plane circular vortex flow. Definition of certain flows, plane circular vortex flow. What are meant by plane circular vortex flows? Usually the word plane circular are not used many times, simply vortex flows, but it is always better to use plane circular vortex flows. The first line of definition of vortex flows, plane circular vortex flows, that is a two-dimensional vortex flows. Rather, plane circular is substituted by two-dimensional vortex flows. These flows are flows where first line of definition, in a polar coordinate system, the velocity field can be represented like that. That means no radial velocity, only tangential velocity. That means a two-dimensional flow field described by with respect to a polar coordinate systems as Vr v theta, its velocity components. So there is no radial velocity, but it has got only tangential velocity. That means the flow where the tangential velocity is only present, but without any radial velocity, are the vortex flow. So therefore, the streamlines will be concentric circles, because the fluid particles moves with circular path only with tangential velocity. So if any particle has got only tangential velocities with respect to any polar coordinate system R, and we can, for example, this is xy, this is r, this is theta. So always there is a v theta, always there is a v theta at different radius, but there is no Vr, there is no radial component of velocity. So now if this be the first line of definition of a two-dimensional vortex flows or plane circular vortex flows, then immediate consequence of it comes from the continuity equation. Let us write the continuity equation. Another thing is that we consider the flow to be incompressible. That is implied. So incompressible flow. So incompressible flow. So if you recall the continuity equation for incompressible flow in a two-dimensional system like this, if we write in terms of the polar coordinate del Vr del r, if you recall, this you will have to recall always, because it is not proper always to derive everything from the basic. So 1 upon r del v theta del theta is 0. This is the form for an incompressible two-dimensional flow in a polar coordinate system, del Vr del r plus Vr by r plus 1 by r del v theta del theta 0. Since by definition Vr is not there, that means it is a situation of flow where only tangential velocity exists. So this two term is 0. So the immediate consequence from the continuity for this type of flow is that del v theta is 0. That means v theta is a function of r only. That means del v theta 0 means v theta cannot be a function of theta. That means v theta is a function of r, which is a very important conclusion. So therefore, we come to the next step, concluding that in two-dimensional vortex flow where only the tangential velocity exists, but radial velocity is 0, in that case the tangential velocity is a function of r only. That means the tangential velocity at different radius, the fluid particles moving in a circular path, where the tangential velocity at any radius is a function of this radius itself. Radius is defined from its origin. That means the tangential velocity is a function of radial coordinate. Now the next question is that what is the form of this explicit functional relationship? What sort of functional relationship with r does the velocity component, the tangential velocity component v theta bear? For that we will have to recognize two types of vortex flow. For that, first we specify a two-dimensional vortex flow. One of those types is free vortex flow. That means it is one of the vortex flow, free vortex flow. The word free poses a different constant. Constant is that it is irrotational. Irrotational. So these are the synonymous. Free vortex flow means irrotational vortex flow or irrotational vortex. Free vortex means irrotational vortex. Or you can say, because already we have discussed that the consequence of irrotationality is the total mechanical energy constant. That means constant mechanical energy. Constant mechanical energy. Therefore, it means that a vortex flow where the total mechanical energy remains constant within the flow, or the vortex flow which is irrotational. Just now we have seen that one is a direct consequence of the other. If we consider a flow to be irrotational, mechanical energy is constant in the entire flow field, or we consider the mechanical energy to be constant in the entire flow field, this will be irrotational. So therefore, either of the two will be valid. That means either of the two we can take, automatically another one will be valid. That means the vortex flow, if it is irrotational or its constant mechanical energy, is known as free vortex flow. And with this constraint, we can find out this explicit form of the function r, that v theta is a function of r. Any one of these, I will show you both the things. First, it is very easy to derive from this irrotationality condition. Now, what is an irrotational flow? Now, in case of an polar coordinate system, you know the rotation is 0. Better we can recall it. I don't know whether I have discussed it earlier or not. Let us see here that in case of a polar coordinate system, how do you define the rotation? Okay, now this is a point, the similar way as we discussed in Cartesian coordinate system. The rotation is like that. Here that is the coordinate r and this is theta. Now at a delta theta, this is the position. Now if we consider a point here and a fluid element, this dotted line. Now this fluid element rotates in this direction. This is the sense of rotation or sense of angular velocity, just like in Cartesian coordinate. This is because of what? So this point, let this elemental length is delta r. So this point has got a more tangential velocity than this point. This is because that v theta is a function of r. So this value is del v theta del r into del r. That means this point has a tangential velocity relative to this. That means this point displaces with respect to this point in the tangential direction by this amount, because v theta is a function of r. Similarly, this point, which is separated by this point by a distance r delta theta or by the angular displacement delta theta, has got a more radial direction displacement or a more radial velocity by an amount del v r del theta del theta. Well, because of the angle delta theta displacement, so this point has got some radial velocity, this point also has got some radial velocity, but the radial velocity at this point is more than this point, because the radial velocity is a function of theta, and that is del v r del theta into delta theta. So this is the displacement. So by virtue of which this dotted element has got a angular rotation in this direction. So now you see this angle is alpha and this angle is beta, and taking this as the positive direction anti-clockwise. So the rotation, the omega z, if we consider this as the z, that means the perpendicular to this, the z, let us consider the z axis, omega about z will be half of the angular velocity. If we take del v theta del r into del r divided by this, so this becomes simply del v theta del r. Well, and this direction del v r del theta divided by r del theta, that means minus 1 by r del v r del theta, or a capital V, I am using this capital V, del v r del theta. So this is in this direction. But there is an additional component which is very important here. This is because apart from this rotation about this point of these two linear fluid elements, the entire fluid elements, anywhere if you take a fluid element, it has got a rotation about this point because of this value v theta, tangential velocity, whose magnitude is v theta by r. That means in any circular motion or curvilinear streamlines, which is always represented in polar coordinate system, where there is a tangential velocity v theta,
it implies always the angular velocity about the origin O, whose value is v theta by r, which has to be always added, and this sense is the positive sense, is a positive v theta direction, so which has to be always added. So therefore the conclusion is that the omega z, that is the angular velocity, the rotation, the average of the angular velocity, the rotation becomes del v theta del r, that cross differential. Just we have seen del v del x minus del u del y in case of a two-dimensional Cartesian coordinate system, del v del x minus del u del y, here del v theta del r minus 1 by r del v r del theta, but only the additional term v theta by r is there. This is the rotation. And similarly, the vorticity is twice the rotation, as I have told. The vorticity is defined as twice the angular rotation, so 2 times, so this is equal to vorticity. Now for an irrotational flow, therefore this will be 0 for irrotational flow, for irrotational flow. So for irrotational flow, this will be 0. So for a recap, I just tell you that how we derive the irrotationality condition or the rotation, the expression for the rotation. So therefore for a free vortex flow, if we start from irrotational vortex, so therefore in a two-dimensional flow, the concept is del v theta del r, that is rotation has to be 0, minus 1 by r del v r del theta. I write the full form first, v theta by r is 0. Now since for a two-dimensional vortex flow this is 0 and v theta is a function of r, so we simply write in terms of the total differential or ordinary differential nomenclature. So del we do not write, because already in our hand it is like that v r 0 and v theta is a function of r. These are already in our hand. Beyond this, we are giving an additional constant, that irrotational vortex. So dv theta dr plus v theta by r 0. So this is the equation, immediately gives the, if you integrate this equation, it gives the function v theta as a r. So how? It can be written as 1 by r ddr of, instead we can integrate it, but we can write this way also, ddr of v theta into r is equal to 0. So if you integrate it, v theta into r is equal to constant. Let this constant is c. That means v theta is equal to c by r. Well, v theta is equal to. So therefore, this is the equation for the tangential velocity distribution, that is a tangential velocity with r, that is inversely proportional to r in case of a free vortex flow. This can also be deduced from constant mechanical energy. I will show you that this can also be deduced from a constant mechanical energy consideration. So what is the total mechanical energy? P by rho plus v theta square by 2. The only velocity is v theta, plus g y is equal to, let this is the total mechanical energy, let this is equal to h. So this is the mechanical energy per unit, pressure energy per unit mass, this is the energy. What is this? Kinetic energy per unit mass, and this is the gy, this is the potential energy per unit mass. Here you can take y or you can take z, better our general notation gz, that is the potential energy per unit mass. So these are the components of the mechanical energy, so total mechanical energy h. Now we know that the mechanical energy remains constant, that means if we take the vortex flow circles, that means for different r, with r the mechanical energy remains constant, that means mechanical energy at this streamline, at this streamline, at this streamline remains constant. That means simply we exploit the mathematical thing, dh dr is equal to 0. So if you make dh dr, first term will be 1 upon rho del p del r. No problem, here also we can get v theta dv theta dr plus g dz dr is 0. But immediately it appears that it is difficult to evaluate the v theta as a function of r, which we got very quickly from the irrotationality condition. I will prefer this, though I have done it in this fashion in my book, but this is different because in my book I gave an expression for the total mechanical energy in a curvilinear streamline. But I think the irrotationality condition, from the irrotationality condition to derive v theta is c by r is more simple, but I will show you from this to derive. Immediately after writing this, it is very difficult until and unless we can substitute this del P del R in terms of the velocity. How can we substitute the pressure term in terms of velocity? Then we will have to take the help of which equation? Momentum equation, that is Euler's equation. If you recollect the Euler's equation in r direction is dVr dt, that means in r directions. Let again the xy like this is r, this is theta, minus v theta square by r, this I discussed earlier, I am not doing it again, minus 1 upon rho del P del R. Here of course I should not show it y, z, because here I have taken z, minus what we will do r direction, so z is positive upward vertically, so this will be minus g cos theta, okay, minus g cos theta. If we consider theta, of course here we consider theta with the vertical, of course you can consider with the horizontal, in that case you will take that g cos theta means it will be g sin theta, minus g sin theta. It depends upon the angle theta you take, because g is acting vertically downward, so g sin theta. If you take this as theta, so it will be g sin theta. All right. Now here dVr dt is 0 because no Vr is there. So minus v theta square by r minus 1 upon rho del P del R is minus g sin theta. So therefore 1 upon rho del P del R, 1 upon rho del P del R plus g sin theta is equal to v theta square by r. Again this g sin theta can be written as dg dz dr, because if this be r and this is this, so this we can write as dz change and this is dr. Well, so this is sin theta, which can be written as dz dr. If we define this as theta, which I have done in my book, so this will be g cos theta, that means the body force in r direction will be minus g cos theta, in this direction the component will be minus g cos theta, then cos theta will be dz dr. Here sin theta will be dz dr. Finally the dz dr will come, which means 1 upon rho del P del R plus g dz dr will be simply substituted by v theta square by r. That means we ultimately come up to the condition of the irrotationality, because irrotationality and the constancy in total mechanical energy is same. That means again this same. That means if you take v theta common, then dv theta dr plus v theta by r is equal to 0. That means the irrotationality condition, dv theta dr plus v theta by r 0, and we arrive as v theta is c by r. So either from irrotationality condition or from total mechanical energy constant in the entire flow field, we get the free vortex flow equation is this, where there is only tangential velocity component and which satisfies the relation with, and it is the function of radius only, a radial location, and satisfies the equation c by r. That means it is an inverse function of the radial distance from the origin. V theta is c by r. Now next task is the pressure distribution in a free vortex flow. Pressure distribution. So pressure distribution in a free vortex flow, if we have to find out, you start from general, that P may be a function of both r and theta. So if one knows the velocity field and if he wants to find out the pressure, the general rule is that you have to exploit the equation of momentum or the equation of motion, conservation of momentum. That means you look to equation of motion where velocity and pressures are linked, so that we know velocity, how can we find out v? Okay, let us see, no problem. dVr dt minus v theta square by r is equal to minus 1 upon rho del P del R. Okay. So now here we see one thing, that dVr dt is 0. So therefore 1 upon rho del P del R. But we should not leave it here. We know that okay, v theta is c by r, very simple, that we can integrate it, but we should satisfy ourselves that this del P del R is equal to dP dr, that means P should not be a function of theta. So if we start from here and write del P del R is equal to v theta square by r, you substitute this and integrate it, it will be little incomplete until and unless we show that P becomes a function of r only. So to prove it conclusively, we consider the theta direction equation of motion or momentum conservation equation. If you recall it, I discussed it earlier is equal to minus 1 upon rho del p del theta. I am sorry, in r direction the equation of motion minus g sin theta will come, or cos theta will come. Sin theta will come if you take, let this is x, this is z, and if we take this as the theta and z is the vertically upwards, that means g acting downward. So this is r theta. So if you consider this vortex motion like this, sorry, tangential like this, so therefore what happens? This g sin theta will come. This is because this constitutes the body force per unit mass in the negative r direction. So g sin theta will come. Okay. So now here you see, what is that? First Vr is 0, so this is 0. What is the value of this? Very difficult to tell it from here. Can you tell what is the value of dv theta dt? V theta is not 0, but will it be 0? It is 0. Why? Until and unless you expand it, you cannot tell it. Just from here it will be confusive. It is confusing that whether it is 0 or not. Though V theta is not 0, but Vr is 0, it will be 0. Why? Because if you expand it, Vr del V theta del r plus 1 upon r del V theta del theta. In 2 dimensional you make it, 3 dimensional jarurat nahi hai, Vz is not there. So if you expand this term, this is the expansion, steady flow. As because Vr is 0, so this is 0. So del V theta del theta 0, earlier it is proved from continuity, V theta is a function of r, which means this term is 0. So therefore the theta direction equation of motion tells us that del P del theta 0. Now we should integrate this. That means after this we can write 1 upon rho dp dr. That means now I can write this del P del r, this del P del r as 1 upon rho dp dr is equal to V theta square by r. And V theta is c by r, that means c square by r cube. So 1 upon rho dp dr is c square by r cube. Alright, now this c square by r cube. Now I can write 1 upon rho dp dr because del p del theta is 0. That means p is a function of r. Now I can write in terms of ordinary differential dp dr and V theta square by r. Now V theta is c by r, c square by r square and r cube. So 1 upon rho dp dr is c square by r cube. Sorry, I am again sorry that this will be minus g sin theta, minus g sin theta, and g sin theta is dz dr. That means minus g dz dr. So this will be always added. Yes, please. Theta direction body force. What is theta direction? Oh well, there will be theta direction body force. Yes. G cos, so this will be balanced by del P del theta. Always. This you can take in terms of P itself. So we don't bother with del P del theta 0 you can write, but theta direction there will be a body force. Yes, very correct. If G is the body force in the r direction, so theta direction there will be also a body force. You are correct. So that will be taken care of G cos theta. So we cannot then exclusively, if we take this, we cannot exclusively tell del P del theta 0. Okay, we can take a function of theta which we can make 0 here. But for this time being we take it as dp dr is c square r cube minus g dz dr. Alright. Well, this we have asked intelligent question that dv theta dt plus vr v theta by r, this is the acceleration in the theta direction, must be equal to 1 upon rho del P del theta and g cos theta. You will see afterwards that this body force term we can take it within the pressure variation. That means the pressure variation in the theta is such that takes care of this g cos theta term. You are correct. So that we can tell that the pressure variation in the theta direction will be taken care of by the gravitational field if we consider in a vertical plane the force vortex equations. Usually we neglect this because the change in the gravitational force within the extent of the vortex motion in a gravitational field is negligible. So either g cos theta or g sin theta is very negligible. It doesn't appear. So usually in many books you will see, I do not know what I have done in my book, that they do not take care of this. They initially tell that consider a horizontal plane. So only they do with del P del r del P del theta. there is no harm. Well, but this is true that g cos theta is there, so del p del theta takes care of g cos theta. So there we cannot tell that dp dr, we have to tell only del p del r, and there when you integrate it, a constant will come which will be a function of theta. But for the time being we just discussed that, we take dp dr is c square by r cube minus g dz dr. Alright, very good. Now if we integrate this, we get p by rho is equal to, with respect to r, that means we integrate this with respect to r, okay. Then what we get, what is the integration of this? Minus c square by 2 r square, r to the power minus 3 plus 1, r to the power minus 2 divided by minus 3 plus a minus 2, minus g z plus a constant, which in case the gravitational force field is prominent, it will be a function of theta. I do appreciate it. So p by rho. So this is the pressure field in a free vortex equation. But most important thing is that if we make a change between two radial points at the same theta, then of course this function of theta will not come. That means if we make a definite integral from 1 to 2, from r1 to r2, so point 1 represents a radial location r1, that means at a radial location r1 to a radial location r2, that means let this be the r1 and this be the r2. So from a radial location r1 to r2, that is r1 to r2, and r1 to r2 corresponds to z1 to z2. So if you integrate it with respect to that z1 to z2, so due to a change in r1 to r2, the elevation changes from z1 to z2, while the theta remains same, So if you make the definite integral, you get p2 minus p1 by rho, rho is constant, is equal to, what do you get it? C square by 2, that is minus. So 1 by r1 square minus 1 by r2 square, minus g into z2 minus z1. So this is the equation. So in case of a horizontal plane, this term will not come, simply p2 minus p1 by rho, c square by 2 1 by. But in case of a vertical plane where the gravitational force are considerable, then g z2 minus z1. If you see that, we can write p2 by rho minus p1 by rho is equal to, then c square by 2 r1 square is v theta 1 square by 2 minus v theta 2 square by 2, because c by r1 is v theta, minus g z2 plus g z1. This is simply p1 by rho plus v1 square by 2, v theta 1 square by 2 plus g. That means writing the Bernoulli's equation, that means an intelligent student will find out the pressure distribution not from integrating the equation of motion, he will simply write the Bernoulli's equation at the two radial points, because he knows for any rotational flow, the Bernoulli's equation with same constant, that means p by rho plus v square by 2 plus gz at one point on one streamline is same as another point in another streamline. That means between two radial locations he can write the Bernoulli's equation. That means this equation is same as writing the energy equations, that Bernoulli's equation at two radial locations. Okay? All right?
Good afternoon. I welcome you all to this session of fluid mechanics. Well, last class we were discussing about the plane circular vortex flows, and then we discussed further about a free vortex motion or free vortex flow. Now, if we recall it, so a vortex flow is described in a polar coordinate system with only tangential velocity as the existing velocity component. That means there is no radial velocity, fluid having only tangential velocity. And immediately we have found that the consequence of continuity tells us the tangential velocity is a function of radial distance, radial coordinate r only. If you consider a two-dimensional case, then if there is no radial component of velocity, only tangential velocity exists. Tangential velocity is a function of r. This is precisely the definition of a two-dimensional or plane circular vortex flow. Now, one of the vortex flows is the free vortex flow. So, there is a this is a generalization. A special case of this vortex flow is a free vortex flow where the flow is irrotational or total mechanical energy in the flow field remains constant. Either of the two can hold good. If one is correct, then other is automatically. When one holds good, other automatically holds good. That means there is a plane circular vortex flow where total mechanical energy in the flow field remains constant, means the flow becomes irrotational. So, irrotational vortex flow where total mechanical energy remains constant throughout the flow field is known as free vortex flow, where we have seen the tangential velocity bears an inverse relationship with r, that is v theta at any radial location r is some constant by r. And then we found the expression for pressure distribution from the equation of motion, and we found it is same as if we derive it from Bernoulli's equation. That means if we use the Bernoulli's equation between 2 points at 2 different radial locations, then P by rho plus V square by 2, here V is V theta square by 2 plus dz1, if we consider the elevation it, if it is in a vertical plane, is equal to the P by rho plus V theta square by 2 plus dz2, that means at the point 2. That means the sum of the three components of energy are same in all radial locations, because the constant total mechanical energy is constant. So, from that on also we can get the pressure distribution equation. Now, after this we must know that there are certain practical situations where the free vortex flow takes place. But one very important consequence of free vortex flow, you see that free vortex flow is that there is no energy added or no energy taken out. That means energy remains constant. So, therefore, free vortex flow exists because of some rotation which was previously imparted on the fluid due to some energy interactions, and just it is maintaining its motion due to some internal action. There is no dissipation of mechanical energy, no addition of mechanical energy, no withdrawal of mechanical energy, it remains constant. So, this type of flow takes place, usually this resembles to certain practical situations. For example, if the water is taken out from a shallow vessel with a from a shallow vessel from a orifice at the bottom, then the circulatory flow which is induced is more or less similar to a free vortex flow, which is often found in our house when the water comes out from a bathtub or from a washing machine. Another case is that if in a whirlpool caused in a river at a far distance from the eye of the whirlpool, the flow field resembles more like a free vortex flow. In a tornado, in an airflow, in a tornado also, the flow of air resembles in some part, in some region, to a free vortex flow. In certain cases like fluid machines, in a pump, the flow at the after the impeller casing, probably you have not read that centrifugal pump, in a centrifugal pump flow coming out from the impeller casing as it enters into the volute chamber, the rotary flow or the rotational flow is similar to a free vortex motion, free vortex flow. Another example is that if you stir a liquid, mass of liquid in a vessel by a stirrer or a paddle wheel, the flow field far away from the stirrer, not very close to the stirrer, resembles to that of a free vortex flow. So, one very important and interesting thing in a free vortex flow is that if you just recall the equation V theta is C by R, where R is measured from the origin, one thing you see mathematically, when R tends to 0, V theta tends to infinity, which means mathematically or physically that there is a singularity at the center. That means at the center there is a singularity. This is the mathematical definition, means velocity is not defined, velocity becomes infinity. What does it mean? That means free vortex flow can never be extended physically up to the origin from where the r, the radius, that is the radial coordinate is measured, which means in practice free vortex motion is never defined at the very near to the origin or at the origin. Mathematically it is undefined. So, what happens in practice, whenever there is a free vortex flow near the center or at the central core,
either there is another type of vortex flow or there is a hollow core. You will see there will be always a hollow core, so that free vortex flow is never extended up to the origin. So there is always a singularity, as it mathematically found that V theta is C by R. So when R tends to 0, V theta tends to infinity. These are all details about the free vortex flow. Now we come to another type of vortex flow, that means the circular motion with only V theta component of velocity, which is known as force vortex flow. This type of vortex flow, the difference is that V theta is directly proportional to the radius, not inversely proportional to the radius. But V theta directly proportional to the radius, for example, V theta is some constant into radius, is very familiar. We are very familiar to it since our school days. This is because we know this is a motion which is exhibited by a solid body. If the solid body rotates, then at each and every point at different radial locations, the tangential velocity is the angular velocity into r. Omega is the angular velocity, so V theta is r into omega. So we know that solid body rotates with same angular speed. That means all points at different radial location rotates with the same angular speed. And as we know, the tangential velocity bears the relationship with the angular velocity as tangential velocity is r times the angular velocity. Omega is the angular velocity, r omega. So which means the tangential velocity is directly proportional to radial location, means the angular velocity remains constant in the entire motion, in the entire field of motion. So in a liquid or fluid, flow of fluid, where V theta is directly proportional to the radius, means that fluid particles moves with constant or equal angular velocities, which means that fluid body moves like a solid body. That's why this type of motion described by V theta is some constant into radial location is known as solid body motion, solid body rotation, or solid body vortex, or forced vortex. So this forced vortex is generated in practical situations when a liquid is taken in a vessel, contained in a vessel. If vessel is given a rotation, if a vessel containing liquid is rotated about its axis, then the fluid body which is being churned with this motion of the solid body executes the rotary motion or rotational motion. That means exhibits tangential velocities which follows a solid body rotation. That means a forced vortex motion, where V theta is constant into the radial location, varies directly with the radial location. Sometimes in certain practical applications, the rotation is important in the fluid flowing through a pipe, enhancing the heat transfer coefficient. So when fluid flowing through the pipe itself is rotated about its axis, then the fluid following a rotary motion is very close to that of a forced vortex motion. So forced vortex motion is a solid body motion where the tangential velocity is directly proportional to radial location or radius.